Hey everyone, today we're going to talk about breadboarding and electronic components. And the term breadboarding comes from the early days of working with electricity when engineers and tinkerers would literally create circuits with screws or nails and some wire on a breadboard. Let's take a look at what it looks like today. So what does a breadboard look like today? Well, there are a couple of examples, and the one on the left here is an example of one that we'll be using in class. The one on the right shows you a 9-volt battery with some components hooked up. And the reason we use a breadboard is it takes a lot less time and money to create a circuit as opposed to a printed circuit board. And because of the cost, printed circuit board really should be used for like a final design. So also what a breadboard allows us to do is we can simulate a circuit. So it allows us to observe how and if the circuit actually even works. So it's really kind of a test bed for us. So it gives designers the ability to change components during development and testing. In other words, you can swap out resistors or capacitors and play around with some of the values of those things. And then finally, it allows us to modify a circuit to easily measure voltage or current or resistance. So let's take a look at how a breadboard works. So if we were to take a breadboard like on the top here and peel away or cut away some of the plastic layers, what you see underneath are really some strips. You have a long strip here, and then which corresponds to the power input or output up here, and then across the rows you see another strip, and they are separated. You need some connections to make those work. So let's explore that on the next slide. So if we take a look at a breadboard like the one we're going to use in class, it's going to look just like this. There are a lot of different kinds, but this is the one that we're going to use. So if you remember from the last slide, where we put our power in is shown right up here. Typically, our positive lead is going to go in this column, and our negative lead is going to go in that column. And as you can imagine, it shows a blue rectangle here. All of those holes are connected via wire. Similarly, if you look at the rows, here you see row 1 and positions A through E, those are connected. And then it skips, and in row 1, F through J are connected. And the holes are really a place to really insert a wire or a resistor or a capacitor or a button or something like that. And it serves to hold those elements into place. So it allows us to create a semi-permanent connection. I say semi-permanent because you can pull them out easily. They're not soldered. Let's talk a little bit about some guidelines and tips and best practices. Here you see on the bottom what's labeled a good and bad wiring scheme. So the wires that you see there are called jumpers or jumper wires, and we will be using those a lot in class. But because we are doing so many different kinds of connections, we're probably not going to be cutting to length like you would see in the good connection. Ours are actually probably going to look more like that, and that's okay. You're not going to get graded on what looks good or bad, just if it works. If you are a professional and you're creating circuits, so you probably want it to look a little bit more like what's on the left. So one of the ways that I like to build circuits is when I'm looking at a schematic or wiring diagram, I'm going to cross off the element on that diagram as I create it. So for example, I'm going to put my power in over here, and then I'm going to cross that out on my schematic, and then I might put in some wires or a resistor or something like that. I'm going to cross those out on my schematic. And then finally, I'm going to have just somebody check it before I even plug anything in to see if it works, just to see if they can explain to me what the circuit is supposed to do. That's really good practice. And next, let's take a look at a couple of the things that we're going to be plugging into our breadboards. One of those things is a diode. And a diode, you might know as a little light, and it's shown in the picture over here, was actually created and invented by a professor from the University of Illinois. Little engineering trivia there for you. And a diode symbol in a schematic looks like this on the left. One thing to know about a diode is that it only allows current flow in one direction. And on the left-hand side here is the positive side, so that's where your current is coming in. And then the negative side, at least on the schematic, is the right-hand side. In reality, the way we tell those apart, if you look at the diagrams, it has two different size wires. So the smaller end is the negative, and the larger end, the longer end, is the positive. So that longer wire is going to be closer to the positive power supply or positive flow of the current. One of the things that you'll want to do, and I'll show you how to do it in class, is to test the diode to see if it works. If it works and you plug it into your circuit, you might try checking if you have the polarity reversed. One of the other things that we're going to use a lot is a resistor. Many of you have seen a resistor, and there's a picture of it here on the right. And if you're looking at a schematic diagram, it looks like a sine wave, but not with round points, with really sharp points, essentially. And resistor's function is to basically control the flow of current. So if you remember back to our water analogy with the pipe or a hose, you can think of a resistor as a rock in the hose or a kink in the hose. So the more resistance, the bigger the resistor, the more resistance you have, the less current you have. And one thing to remember is that the units of resistance are ohms, as the little Greek letter omega that looks like the horseshoe, and it's named after George Ohm, whose Ohm's law is V equals IR. And it's good to know that there are some different kinds of resistors. Even though if you look at all four of these kinds of resistors and their schematic symbols, they're all pretty much the same except the variable resistors. And the variable resistors you see here on the right, the upper right, those are meant for smaller circuits. And you may be familiar with these if you have maybe like a dining lamp or a lamp or a chandelier in your home that you can dim. You have a dimmer switch. It has this type of resistor in it. Now that has a slightly different symbol to it, and it looks like the regular resistor with an arrow pointing to it. There are surface mount resistors, which we're not going to use, 5-band carbon resistors, which we're not going to use. We're going to use the carbon film resistors with 4 bands. And there's a reason for the 4 and 5 bands, and it has to do really with identification. So the codes or the color codes on the resistor are really used as a visual to help us determine how much resistance it is. I'll get back to that in a second. My favorite way is to just use a multimeter, and there is a separate presentation on how to use multimeters where we'll go over that. But for now, let's get back to the color code. All of the different colors and the number of bands mean something. So let's take a look at what those mean. Well, here's what those color bands mean. So take a look at the cartoon, if you will, up at the top. This gives an example. So you read it from left to right. And I want you to take a look real close at the cartoon or the schematic, and then take a look at the real thing. So if you read the cartoon, it reads left to right, first and second band, a multiplier, then there's a large space, and then there's another band for tolerance. But if we look over here, Boy, there aren't a lot of spaces here or here. These are really kind of hard to read, in my opinion, unless you do it all day, every day, and get good at it. I don't know about you, but I'm not. I like to use a multimeter. But let's take a look at this and figure out how it works anyway. Let's look at an example. So in this example, my little cartoon at the upper right has 3 bands and it has a tolerance band. So if I look at the first band, that's brown. So I go down and find brown and that's a 1. Second band is black and that's a 0. So I have 1 and a 0, that's 10. Then I have a multiplier that's red. So I have 10 times 100, or that's 1,000. And then I go to my tolerance band, and it is gold. It only comes in gold or silver, or there's nothing there. So here's how that looks. I have 10 times 100, which is 1,000 ohms, and my tolerance is plus or minus 5. So we would write that as 1 k ohm or 1 kilo ohm.